Jai Hind everyone. I am Ankita Sharma. I am working here as an assistant professor in EC department. So today we are going to cover the ST solution part 2. Part 1 we have covered already. So the remaining questions of ST will be covering today only. So in last lecture we have discussed till question number 7th of section B, the interfacing of RAM and ROM with the 8085 microprocessors. Now the 8th question is differentiate maskable and non-maskable interrupts and draw the 8085 interrupt structure. So if you see the university pattern of the questions, interrupt questions are always there in the paper. 8085 interrupts. As we all know, there are two types of interrupts, maskable interrupt and non-maskable interrupt. As the name suggests, maskable interrupt is an interrupt to which you can put a mask, just like you can put a mask and stop that interrupt to interfering in your main program of 8085 microprocessor. And in non-maskable interrupt, it happens like you cannot mask that particular interrupt, and that interrupt you have to service that particular interrupt. So if we have to create a differentiate between maskable and non-maskable interrupt, in maskable interrupt, the interrupts that can be enabled or disabled by the user, by the microprocessor, we can enable interrupt or disable interrupt according to the wish. And the instructions like enable interrupt, disable interrupt, and SIM. SIM is set interrupt mask. This is also a very important instruction if we see the instruction set of 8085 microprocessor. And CPU can ignore these interrupts because it depends on its wish. If the microprocessor is free at that particular time, then the microprocessor will be servicing or will be entertaining those interrupts. Otherwise, the microprocessor will be masking those interrupts. They are eligible to be masked. So there are 4 types of interrupts that are maskable interrupts: RST 7.5, RST 6.5, RST 5.5, and INTR. INTR is having the lowest priority. Lowest priority means this is the lowest priority. If suppose we have 2 interrupts, INTR and 6.5, RST 6.5. If these 2 interrupts come at the same time, then the microprocessor have to choose out of these 2 on which interrupt the microprocessor will provide a service routine. For that, there is a priority order, and INTR is interrupt request is having the least priority order. Next is non-maskable interrupt. In 8085 microprocessor, there is only one interrupt, that is trap, which is non-maskable. If the interrupt trap comes in between the microprocessor's program, then microprocessor have to stop or halt, or you can say pause its programming, pause its work. It will first service the trap interrupt, and after that it will resume its working. But this trap, as the name suggests, the microprocessor will be trapped and it has to service this interrupt. And as being the highest priority interrupt, trap is resolved on priority also. So this is non-maskable interrupt, and if we see the difference between the interrupts, we can closely look here. This is a table which we have prepared. If we saw the meaning, interrupts which can be disabled by the CPU or which can be disabled or enabled, or I can say it can be masked, are maskable interrupts. Which cannot be disabled or masked are non-maskable interrupts. For example, RST 7.5, 6.5, 5.5 INTR, and here it is trap. If I talk about the masking control, who can control these interrupts? Who can mask these interrupts? So the control can be used by enable interrupt. By enabling interrupt pin, I can enable the interrupt or disable the interrupt by using DIE. Next is SIM. SIM means set interrupt mask, which is of 8-bit, and trap cannot be masked by any software. Nothing can stop the interrupt trap. If I talk about the priority in non-maskable and maskable, maskable interrupts have the lower priority as compared to the non-maskable interrupt trap. Trap is the only non-maskable interrupt. If we can say this also. Can CPU ignore? Yes, CPU can ignore the maskable interrupts if we have masked those interrupts, but in the case of trap, or I can say non-maskable interrupts, microprocessor or CPU have to accept it. There is no option to stay away from this interrupt. Trigger type, if I talk about the trigger type, the clock type, there are 2 types of triggers. One is edge triggered and another one is level triggered. So if we see the diagram of this. This is level triggered. There is some level. This is level triggered and this is the edge triggered, rising edge or falling edge. So this is edge triggered and these are level triggered. Two types of triggered are there. So RST 7.5 is edge triggered. RST 6.5 is level triggered. RST 5.5 and INTR, these three are level triggered. And if I talk about trap, it is level plus edge triggered both, because it is very reliable. You cannot mask this interrupt. That is why if it is level or edge triggered, it will go. Vectored interrupts are those who are having there some address, vectored address. It is vectored. RST 7.5, 6.5, 5.5 are vector interrupts, and INTR is a non-vectored interrupt. So, and if I talk about the trap is also a vector interrupt having an address 0024H. H is an exact decimal number here. And use case, normal input output operations are used for non-maskable interrupts, maskable interrupts, and for non-maskable interrupts, emergency situations. In emergency situations, these interrupts are used. So this is the interrupt structure. As you can see in the question, there was a question, draw the 8085 interrupt structure. This question is very important. So you can see here, we are having all the 5 interrupts here, RST 7.5, 6.5, 5.5, trap and INTR. So first we have to just write down the priority order. Trap is having the highest priority, then 7.5, 6.5, 5.5 and least priority is having the INTR. So after putting these, just put the trigger, which type of trigger it is, edge triggered, level triggered, level triggered. Trap is both triggered, level and edge both, and INTR is level triggered. So what we have to do, we are putting a AND gate here for INTR, and there is a SR flip-flop for interrupt request. We have to enable this interrupt. I am having enable interrupt, disable interrupt, reset pin and any other interrupt to activate this OR gate, and this OR gate will further give its output to the reset pin of SR flip-flop. Further, the output of this SR flip-flop will enable the AND gate here, and we will be having the interrupt service routine addresses for the from the external device. As we can see, we are having 8 software interrupts also, that is RST 0 to RST 7, and every RST here is having its personal vectored address, and this address is fixed. We cannot change the address. Next is trap. You can see a straight line here and the address is call 0024 because trap is not stopped by microprocessor. We have to deal with the trap. That is why it is call 0024. For RST 5.5, there is a mask pin M5.5 which has been taken from SIM instruction, and its address is call 002C. If we see here, the input, this Q, SR flip-flop's output is going as an input in AND gate for INTR and for RST 5.5 also. For RST 6.5, mask pin for 6.5 is written here, and same Q output is also given as an input in AND gate, and we are getting the address, vector address for these interrupts also. For RST 7.5, as it is edge triggered, that is why we are taking a delay here, D flip-flop, and it is also having the clear pin which is having the RST 7.5 and reset 7.5 by SIM instruction. These instructions are used to change the values here. So 7.5 and all the one input for AND gate is coming from the SR flip-flops output here. So this was the interrupt structure for 8085 microprocessor here. The next question was question number 9. Discuss the functions associated to the 8085 instructions. These are some instructions which were also given. Stacks, push, SBI, CMA, RAR, RSTN and JNC. We'll discuss it one by one. First of all, STAXRP. STAXRP means store the contents of accumulator. X means on the register pair indirectly. As we can say here, the store the contents of accumulator will be stored indirectly. What do you mean by indirectly? Because here we are not having any memory address, we are having a register pair. So the register pair contents will behave as an address, and at that particular address the contents of accumulator will be stored. So STAXB means accumulator's content will be stored in the memory location pointed by BC. For example, we can take it an example also. BC register pair is having contents 2500. So this 2500 further, this 16-bit number will act as a memory location, and at this particular memory location of 2500, the contents of accumulator will be stored. So that is why we can say this is a indirect register indirect addressing mode. Next is, as we can see, this register pair here can be BC register pair or DE register pair. We cannot use HL register pair here, and no flags will be affected here. Next is push RP, push register pair onto stack. The contents of the register pair out of these four combinations, BC, DE, HL and PSW is flag register. The contents of these registers will be loaded to the stack, and further it will be decremented by 2 because we have filled the space of the stack for 2 locations for 2 bytes. That is why there will be decrement of 2 bytes. Because 2 bytes of data we have pushed into the stack. That is why there is a decrement of 2. But if we have to pop the data, it will be increment by 2. This is a basic difference between push and pop for stack. Next is SBI, subtract immediate with borrow. What we have to do here is an example, SBI 10H, subtract the contents of accumulator and the immediate data which is given here 10H, including the carry, the 8-bit immediate value and the borrow from the accumulator. We have to subtract it, and the result will automatically be stored in the accumulator, as this is a condition for all the arithmetic, data transfer and logical operations or instructions in the 8085 microprocessor. So all flags will be affected by this. So we can take an example here also. Suppose we have to do SBI 10H, accumulators contents are 0EH and the carry or the borrow is 0. What we will do? 0E minus 10 minus 00. So E we all know is 14. 14 minus 10, 10 is 16 here. So it will be negative, or we can take it 1 also here. It will be more easy to understand. We can take 1 2H. So 12 minus 10 minus 0. So it will be 0 2H. So this will be stored in the accumulator. This is the operation which will be followed by SBI immediate data. Next instruction is CMA, one of the simplest instructions which is used to just complement the contents of accumulator. Suppose the contents of accumulator is 0 1H. So I can write 0 1 in binary like this, and we have to just complement, or I can say put a NOT gate here. So the value will be 1 1 1 1 1 1 1 0. So this will be the new value for the accumulator, and the contents will be stored in the accumulator itself. Next is RAR. One of the most important instructions is rotate instruction. Here it is written RAR, rotate accumulator right through carry. As C is not written here, it is not included in the opcode, but the contents will be moved to right with carry. So here we can make a carry here. We can put 8 bits, 1 2 3 4 5 6 7, and this is 8. D0, D1, D2, D3, D4, D5, D6 and D7. Suppose I am taking the contents of accumulator is 18H and the carry is 1. So this is 1, and 18 can be written as 0 0, 0, 1, 1, 0, 0, 0. When we have to rotate it through right, that means this D0 will move to the carry flag and this carry flag will go to the D7 and every bit will be shifted to right. Every bit will be shifted to its right here like this. It will be shifted to its right. Bit by bit shifting will be there and now the new values will be 0, 1, 0, 0, then 1, 1, 0, 0. So the answer is this and this. This is Z8 and this is 8C. 8, 4, 2, 1. This is 12 and 12 is C and the carry is now 0. So this is rotate right through carry. Next instruction is restart instruction RST-N, which we have used in interrupt structure also. RST3 jumps to the address 0018. Now from where this address is coming, you can see in the interrupt structure RST3 is having the address 0018. As these addresses are fixed, that is why the address will be provided directly. It fixed memory n into 8, the vector into 8. RST2 will jump to 0010, RST7 will jump to 0038. This is fixed. This is a software interrupt instructions and we have 8 software interrupts here. Next is JNC, which is jump if no carry. This is a kind of branch instruction and we can say conditional branch instruction. The instruction on which there is some condition applied. Here we can say jump if no carry. It will jump, it will transfer the program control to that particular specific address which is given in the instruction only when the condition is satisfied. And what is the condition here? That jump if no carry. If the carry is not there, only then it will shift the control. So this is a conditional jump. Jump occurs only if when Cy is equal to 0, when carry flag is having 0. If carry flag is having 1, the program continues normally and no other flag is affected. For example, it is written JNC 2050H. That means jump to the memory location 2050 if there is no carry, only in that condition. Now the next question is from section B, is question number 10. Draw and explain the architecture of 16-bit microprocessor. So 8086 microprocessor is a 16-bit microprocessor because it is having a data. The data we can transfer at one machine cycle is of 16 bits and the address lines here are used are 20 bits. So that is why it is a 16-bit 808586 microprocessor. 8086 microprocessor. If we look at the architecture, this is the architecture, and if you see the dotted line, the architecture is further divided into two parts. This is BIU, that is bus interface unit, and this is EU, the execution unit. So this is the outer part where we are dealing with the memory and the input output. Here there are some blocks. This is the 6-byte prefetch instruction queue. This question also was there in section A in 2 marks. What is the use of prefetch queue? This 6-byte queue is the reason that parallel processing is possible in 8086. If I have removed this 8086 prefetch queue, then there is no possibility of parallel processing, or I can say there is no possibility that BIU and execution unit both works parallelly. This is the main reason behind the 8085 being a fast microprocessor. So this is a summation which is used to calculate the physical address. The physical address can be calculated from here. These are some registers. These are segment registers, code registers, stack registers, code segment, stack segment, data segment, extra segment, and this is instruction pointer. Instruction pointer is just like the program counter, it just points to the instruction on which the current program is there, the current location is there, and these components, these 2-3 components are a part of bus interface unit. This is called a bus interface unit, and the other block is execution unit. Bus interface unit performs all the bus operations. It can fetch the instruction, read and write the operands from memory and input output, and it calculate the addresses, the physical addresses of the memory operands, and this instruction bytes are transferred to the instruction queue. These are transferred to the instruction queue here, and from instruction queue it will go to the execution unit, which is having the control unit, and execution unit is doing the execution part. It is decoding and it is executing the particular instruction, and this is possible due to the help of pipelining. And if we see the structure of pipelining, I can just share here. Suppose I am having 3 instructions. I am having 3 instructions to be executed. There are 3 instructions. So first of all, this instruction will be fetched, then executed. For that, suppose we have fetched first instruction, and when first instruction is fetched, it will go for the execution. Meanwhile, the first instruction is gone for the execution. The fetch unit, the BI unit is this unit, this particular unit, BIU unit is vacant. In that case, parallelly, when the execution of first instruction is undergoing, the second instruction will be fetched here, and the fetching of second instruction is done. The execution of second instruction will be started, and the fetching of third instruction will be done here parallelly, and when this is done, so on. So if we see here, parallelly things are happening. This is a parallel process. That is why there are 2 segments here, because we can do pipelining and we can have a parallel processing, which is the main reason why 8086 is called a fast microprocessor, fast processing. And BIU contains instruction queue, segment register, instruction pointer and address adder, and execution unit is also having control unit, instruction decoder, ALU, pointer, index registers. These 4 are general purpose registers. All the registers here are of 16-bit each, because the data stored is also of 16-bit. That is why we are having 16-bit registers here. AX is our accumulator register, BX is our base register, CX is our count register, and DX is our data register. Further, SP is stack pointer, BP is base pointer, and these are 2 instruction index registers named as source index and destination index. And here it is ALU. ALU we all know is a arithmetic logical unit, operands and flags. Here we are having 16-bit flag, 16-bit flag register. Total 9 flags are there. Now section C, which is having 7.5 marks for each question and total 15 marks. So the 11th question is, draw the 8085 microprocessor architecture and explain timing and control unit. So this is the architecture for 8085 microprocessor. As we all know, 8085 microprocessor is an 8-bit microprocessor, because at one cycle only 8-bit of data can be transferred, and the size of address bus is of 16-bit. If we closely look at the block diagram of or the architecture of microprocessor, number of questions, small questions for 2 marks, for 7 marks, many questions can be covered from this particular block. Also, we can have the programming model. So this portion can be known as the programming model. The timing and control unit can be further discussed alone, just like in this question. You can see, explain the timing and control. This is the only portion we have to discuss. These are interrupt controls. Here all the interrupts are discussed. INTR is interrupt request, INTA is interrupt acknowledgement, RST 5.5, 6.5, 7.5 and trap. All the maskable and non-maskable interrupt control is here. Here it is serial input output control for serially input and output, serial data in, serial out data. There is an 8-bit internal bus, and here there is address buffer and data address buffer. So if I talk about from the basics, in 8085 microprocessor, the data size or the data bus size is of 8-bit. This is my data bus. The address bus is of 16-bit. I have a full video lecture recorded. I have recorded a full video lecture for the 8085 microprocessor also. So you can see all the minute details from that also. For a brief discussion, we can come here. And for detailed version, you can go to that video lecture also. So here we are having different registers pair. W and Z are temporary registers. B, C, D, E, H, L, these are 6 general purpose registers. We can club these 2 register to make a register pair. So we can say we are having 3 register pairs. 3 register pairs. All the register pairs are of 16 bit each. W and Z can also be combined as a temporary register and can be used for a 16 bit data. 16 bit data के लिए हम ये यूज बहुत आराम से कर सकते हैं. We are having stack pointer which is used to point to the stack, to the top of the stack. We are having the program counter which keeps on counting on which memory location the microprocessor is there right now. Increment and decrement used for the address and data buffer. So this is the instruction register. Instruction register will have the instruction. Next is instruction decoder. It will decode what kind of operation is to be performed on that particular thing, and on depending on that it will transfer it to ALU, which will be used for all the arithmetic and logical operations. Then there is flag register. 8-bit flag registers are there. Temporary registers which is shown here, and accumulator is the special register. All the accumulator, this particular accumulator is of 8-bit. Accumulator is of 8-bit in 8085 microprocessor, and all the result of instructions of the instruction set of the operations of arithmetic logical units and everything will be stored in the accumulator. All the results are automatically stored in the accumulator. So this is a timing and control unit. Timing and control unit is having multiple pins here. We can see X1, X2 are frequency generated pins. Clock out, ready, write, read bar, write bar. ALE is address latch enable. S0, S1 and IO space M bar are status signals. Hold pin, hold acknowledgement. Reset in, reset out. These 2 pins are used for DMA control. When DMA wants to interface with microprocessor, these pins are used in that case. Otherwise, there is no use. If there is no DMA, then hold and hold acknowledgement pins are not used for only microprocessor. This is reset in. When we have to reset in or reset out, this reset pin is used for that. These are status pins. S0, S1 input output / memory bar, by which external source microprocessor is taking the data. It is taking it from input outputs or it is taking it from the memory. That is why we are using this. Next is control pins. Control pins is read bar, write bar. Microprocessor is reading from somewhere, writing from somewhere, and ALE. ALE pin is very important because as you can see here also, address data lines are multiplexed. I can say AD0 to AD7. We can see A and D both are there. That is multiplexed lines. Address, lower order address and data lines are multiplexed, and when this particular pin will act as an address line or a data line, this is decided by ALE pin. When ALE is 1, address will go. When ALE is 0, data will go. So this is the pin for timing and control units. This is the control signals bifurcation. We can see it from here. There are 3 control signals. Read bar is used to select that microprocessor wants to read from the memory. It is memory read, or from the input output. If it wants to read it from the input output port, then it will be known as IO read. Similarly with write, it will be input output write, input output read. For memory, it will be memory read, memory write. These all pins are extra here. Interrupt acknowledgement, halt, hold, reset. And this is the last question. Question number 12. The programming part. Write an assembly language program for multiplication of 2 8-bit numbers in 8085 microprocessor, and also specify the addressing modes associated to the instruction. If we closely look here, it is written multiplication, and we all know in 8085 microprocessor there is no provision of multiplying the 2 numbers directly. There is no such instruction for multiplication, so we can do it by the method of repeated addition. Suppose I have to multiply 2 numbers, then we will just multiply that 2 numbers by repeatedly adding those numbers. For that, I need 2 numbers. Out of these 2 numbers, one number is stored in 3501H and the second number I am storing at memory location 3502H, and the result I will be taking from the accumulator at 3503H. So first of all, starting with the first instruction, load HL pair immediately with 3501. That means the first number will be at 3501, which is my multiplicand. Okay, after that the contents of M are stored in B. M is the memory pointer for HL pair. That means the first number is indirectly present in M memory pointer will be copied to register B. Now B is having our first number. So first number is in B register now. After that I have to move to next instruction or the next memory address, which is 3502. For this we have an instruction INX, increment in HL pair. So HL pair contents will be 3502 and similarly it will be pointed by M memory pointer, and now M's contents will be copied to C. B is having the first content, C will be having the second number. Now what we have to clear the accumulator because there must be some garbage value in the accumulator. Now we have to clear it. So we have cleared microprocessor here. We cleared the accumulator. Now it is add B. What is exactly happening? For addition, one number should be there in the accumulator. So we have just cleared accumulator with 00H. The contents of accumulator is 00. Now the contents of, suppose I am multiplying 02 with 04H. These are the two numbers on which I am applying the multiplication. So B is having 02. What is exactly happening? We are just adding these two. We are adding these two. The answer will be 02H, automatically stored at accumulator. Now it will decrement the contents of C. C is having the value 3 now after the decrement, because we have done the decrement. 4 minus 1 is 3. Again jump if not 0 to 2008 memory location. We have to check the contents of register C. Here this is C. The contents of register C is 03 and the conditional jump instruction is here, which is jump if no 0. As we see, this is not 0. That is why it will jump to the loop here, to the loop, and it will again add. Now accumulators contents are 02. Accumulators contents are 02. It will be added with B. B's contents are also 02. Similarly, this will again and again repeat till the contents of C register are 0. When the contents of register C are 00, it will after that store the contents of accumulator, and at that particular point accumulator contents will be 08H. 2 multiply 4 is 8 and we have to multiply, we have to repeat this addition 4 times. That is why, so 1, 2, 3 and 4, these 4 times, and this is the last thing. So we have to just store the data. So B holds the multiplicand, C holds the multiplier, A starts from 0. We repeatedly do A plus B until C becomes 0. This is the conclusion here. Final accumulators contents are stored in 3503 and these are the addressing modes. LXIH, immediate addressing mode because immediate data is given, 16-bit data is given. Move B comma M, indirectly we are having the contents of register. B is having the indirect contents. INXH, register pair is there, in implicit is this. Move C comma M, register indirect. MBI is immediate. Add B, register. DRC is also a register addressing mode. JNZ is direct conditional instruction. Direct addressing we can say. This is also direct addressing, and halt is implied addressing mode. So this is the program for multiplication of two 8-bit numbers. This is a very important question that generally comes in exam. Similarly, which we have covered in multiplication, we can also do the division part by repeated division, repeated subtraction. Here the division can also be done. Multiplication was done by repeated addition. We are again repeating the addition, and for division what we have to do, we have to just subtract the numbers one by one till the counter. So these were the addressing modes covered with these instructions. Thank you.